Hi, this is the third segment of review for exam 3, Chem 112. I would like to go over a practice problem, and this is practice problem number 10. Now the question is, under standard states, just to remind you, under standard state means 1 atmospheric pressure, and if I have a solution, 1 molar concentration of the solution, and temperature is 298 Kelvin. So that makes the standard states. So under standard state, predict maximum electrical work. Maximum electrical work. That means how much electrical work you can get from a particular voltaic cell. Maximum electrical work that you can accomplish when 75.0 gram tin SN is consumed. Now what is the reaction given? SN solid plus I2 solid, giving SN2 plus aqueous plus 2I minus aqueous solution. So let me read this question again so that you all understand it. Under standard state, we want to get maximum electrical work when 75 gram of tin, SN, is consumed in this reaction. This is electrochemical reaction. If this question is given to you, first you need to think about, how do I calculate maximum electrical work? So let me write down here. W max, maximum work, would be given by delta G value. Under standard state, that would be delta G0. So delta G0 not only tells us whether a reaction is spontaneous or not, it also tells us maximum work you can get out of it. So in this case, delta G0, and that would be given by minus NF E0 cell. This is the cell voltage. So basically, these two numbers will be coming. This is a fixed number, 96,500 coulomb, and any number of moles being transferred from one half cell to the other half cell in this particular electrochemical reaction. So first thing is we have to split that reaction into two half reactions. Tin solid giving tin 2 plus. Same number of tins so that I don't need to multiply by anything, but then I need to balance the charge, 2 electrons. And I would have I2 and I minus. I2 solid, that's giving 2I minus aqueous. Again, I have 2 minus 2 charge on the right hand side, no charge on the left hand side. So I must have 2 electrons added on the left. So now my charges are balanced. Now, even though this question is asking for maximum work, I'm also going to explain to you the meaning of these oxidation potential, reduction potential, how do I get them, so that way you'd have a broader understanding and you can answer not only this question or any other related question. Now, this is the oxidation where electron is given off. So whenever electron is released in a reaction, that's oxidation reaction. Oxidation. And this is receiving electron. Receiving of electron is called reduction. So oxidation process, electron is given up. Reduction, where electrons are absorbed. You can see electrons are absorbed. Now 2 moles of electrons are being transferred from one half cell. This is one half cell to another half cell. So this is n equals to 2. So from here I can get n equals to 2 to plug in into this expression. So this is oxidation. If I ask you a question about which one is anode and which one is cathode, say add it to this question, anode would be this one where oxidation takes place. And in my lecture note, I wrote this for you to remember, ox, anode oxidation. And I also wrote down here, red, cathode reduction. So this would be acting as a cathode in a voltaic cell, cathode reduction. So basically and also we need to have these E0 values. This is an oxidation reaction, so I can write down E0 oxidation. Book usually gives you all the reduction values. So if you look at the reduction values, you're going to get minus 0.136. So this is same, so you have to change the sign. E0 reduction, and in this case, is going to be 0.136. Book has minus 0.136, and oxidation, because those are reduction values, so you switch the sign, so the negative sign becomes positive. And so let me explain this to you. That book has this value, let me write down here, not to confuse you. This is 0.136, and the book value from book, we are going to get E0 reduction equals to minus 0.136 volts. Why we change the sign? Because the reduction value is given, and we're looking at the oxidation, because this is an oxidation process. For second half reaction, you can just get the value as you see in the book, and that value is 0.536 volts. So when we add up these two reactions, electron would cancel out. That's like being transferred from one half cell to the other. Sn plus I2 solid giving Sn2 plus, this is aqueous, Sn2 plus aqueous plus 2I minus aqueous, and E0 cell equals to E0 oxidation plus E0 reduction. This is the cell voltage under standard state. It has contribution from oxidation. This is the contribution from reduction, or contribution from anode, contribution from cathode. I often compare it with a football game where, in this particular case, tin here on the left-hand side is releasing 2 electrons, is transferring 2 electrons. These are the 2 electrons. And what is receiving those electrons? I2. I2 is receiving those electrons. So here the process is Sn is giving up 2 electrons, and iodine as a receiver is going to receive the electrons. So tin is undergoing oxidation, iodine is undergoing reduction. Now, large oxidation number means how readily it can give up electrons. Large reduction potential means how readily an element can absorb electrons. So by looking at those numbers, you can decide whether it's a good receiver or a bad receiver of electrons. We often talk about oxidizing agent and reducing agent. So let me write down those two things. Oxidizing agent and reducing agent. Let's write down here. Oxidizing agent, and we are also going to mention about this reducing agent. We are going to also define oxidizing agent and reducing agent. Oxidizing agent is the one that helps in oxidation. In this case, if iodine were not there, tin would not be giving up its electrons. So what is helping in oxidation? Iodine. So even though iodine is being reduced, but is helping in oxidation of tin. So this is going to be oxidizing agent. The agent means the one that helps in oxidation. It's like a receiver. If there is a good receiver, then the quarterback is going to throw ball. In this case, we're looking at electron ball. Now, if there is no receiver, there will be no such ball thrown. So in other words, in this case, iodine is the one who is receiver and is helping tin to throw the electrons or undergo oxidation. So tin is going to help in the reduction process by throwing the electrons. So this is going to be a reducing agent. So reducing agent is that chemical that helps in reduction process. Now here, tin is helping in the reduction process by throwing the electrons. Because if it doesn't throw the electron, there will be no acceptance of electrons on the other side. So I must explain this to you again, that don't get confused between oxidizing agent and reducing agent. Oxidizing agent helps in oxidation process. Reducing agent helps in reduction process. Reduction means acceptance of electron. Oxidizing agent itself gets reduced. Reducing agent itself gets oxidized. So make sure you understand the difference between these two statements. Okay, now we got these half cell reactions. So let's now get the value. E0 oxidation and E0 reduction, when you add them up, I get 0.672. You add these two numbers. 0.672 volt. So that's our E0 cell. Now we can now plug in these numbers into this expression. I have 2 moles of electron, 2 mole electron times 96,500 coulomb per mole of electron. Faraday, 1 Farad is 96,500 coulomb per mole of electron. That means if you add up all the charges carried by 1 mole of electrons, then that would be 96,500. So 96,500 coulomb per mole of electron times 0.672 volt. That's 0.672 volt. Now, this is what I got. Minus 1.30 times 10 to the power 5 joule. And now I can get it in kilojoule divided by 1000, and then I get 130.0 kilojoule. So that's the kilojoule of the maximum work you get provided this reaction happens where you have 1 mole of tin consumed. So I should write down here per mole of SN consumed. But in this particular case, 1 mole of tin is not consumed. So find out how many moles of consumed tin is consumed. So from gram, you calculate the mole. So I'm going to show you the next step. Number of moles tin consumed would be given by 75.0 gram tin times, by looking at periodic table, we find out 118.7 gram per mole, and that gives me 0.632 mole of tin. Okay, now I can get my final answer. This is kilojoule, this is kilojoule per mole of tin. Now we have that many moles of tin, so I need to make more space here. So my last part of this calculation, I'm writing down on the top. So W max will be given by minus 130 kilojoule per mole of tin times 0.632 mole of tin. And that gives me I'm just going to write down this answer, minus 82.2 kilojoule. So that's the maximum work you can get from this voltaic cell. Now why negative? It's negative because it's the spontaneous process. This is a voltaic cell. Once you combine those two ends, positive and negative, anode and cathode, there'll be flow of electricity. And that's why there's a negative. So spontaneously you get electricity out of this. Now I'm going to do practice problem 11. Okay, this is going to be practice problem number 11. Let me give you a series of reactions and their reduction values. E0 reduction value for first reaction is plus 2.87 volt, and the reaction is F2 plus 2 electron, giving 2F minus aqueous. The next reaction is E0 reduction equals to plus 0.77 volt, Fe3 plus aqueous, plus aqueous means water solution, electron, that gives you Fe2 plus aqueous. Now for the third reaction, E0 reduction equals to minus 0.76 volt with zinc 2 plus aqueous plus 2 electron, giving zinc solid. Okay, this is the given information. The question is, which is the most likely to undergo reduction reaction? Let's call this reaction 1, reaction 1, reaction 2, reaction 3. For A, I'm going to ask 3-4 questions from this set of values. So for this half cell reaction, reaction value is this. For this second half cell is 0.77, third is minus 0.76. So the question is, which one is most likely to undergo reduction reaction? Most likely to undergo reduction out of these three. Basically, in a simple analogy, I can say, we're looking at acceptance of electron. Which one can best accept electrons? Or which one could be the best receiver of electrons among the three? Answer is straightforward. You go by the value, positive value. The largest possible value means the best acceptor of electron. So 2.87 is the largest value, and that means this particular reaction would show maximum, it would be more readily accept electrons. So reaction 1 is the one which would readily undergo reduction reaction. So I'll call it, answer is reaction 1 because of the largest value of reduction potential. Question B, if I can ask you which is most likely to undergo oxidation. Most likely to undergo oxidation. This time we're not asking about reduction. Reduction is acceptance of electron. Most likely to undergo oxidation. Oxidation means throwing of electrons or loss of electrons. So we're talking about reverse process. So one way to understand this would be change this to oxidation values for the reverse reaction. If I go for oxidation values, let's write down their oxidation values. When the reduction value is this corresponding oxidation value is just the same number, but the sign gets changed. Minus 2.87 volts. For the second reaction, corresponding oxidation would be minus 0.77 volt. For the third one, plus 0.76 volt. Again, here we're looking at the oxidation or the best quarterback, which one can best throw electrons. So if you're looking at the largest possible oxidation values. So this has the largest possible oxidation values. So my answer to this question is reaction 3. So for looking at the best receiver of electrons, you look at reduction values, the largest reduction values. For best oxidation, which one can most readily undergo oxidation or throw electrons more readily, you look at oxidation values, the largest oxidation values. And that's how we got reaction 3. C, which one is least likely to undergo oxidation? Rather than saying most likely, we'd now call least likely. Least likely to undergo oxidation. Least likely to undergo oxidation. Most likely, we go by the largest number. Least likely, obviously the smallest number. This is the smallest number. Negative 2.87 is the smallest value. Negative means worse than this. I mean, this is worse than 0.76 minus 0.77 minus 2.87. So this would show the least likely to undergo oxidation, because that's the smallest oxidation number. So I'll write down reaction 1 as an answer. So most likely oxidation reaction means you look for the largest value. Least likely to undergo oxidation, you look for the smallest oxidation value. And the fourth question that I'm going to attach to this would be part D. Least likely to undergo reduction. Likely to undergo reduction. So which one is least likely to undergo reduction? Again, the question is about reduction. So look at the reduction values. The largest one gives you most likely to undergo reduction. Obviously, the smallest value would give you the least likely to undergo reduction or accept electrons. So this is going to be reaction 3. I can add one more to this. The strongest oxidizing agent. The strongest oxidizing agent. Just a few minutes ago I mentioned about oxidizing agent. The agent that helps in oxidation obviously is the oxidizing agent, means helps in throwing off electrons by another element. So it must be a good receiver. The best receiver would be the strongest oxidizing agent. Best receiver means you look for reduction values. The largest reduction value would be the best receiver. So this is the best receiver with largest reduction value. So that's going to be reaction 1. So make sure you understand this concept before you move to the next practice problem. Next one will be practice problem number 12. Okay, this is problem number 12. Now this is on entropy calculation, and let me first give you the question right of the reaction. 3O2 gas forming 2 ozone gas, and what is given is delta H value. Rather than giving a value, we're just saying that this is positive or greater than 0. So delta H is greater than 0. Now, tell us about whether this reaction is going to happen spontaneously or not. If it is not happening spontaneously, at what temperature it would happen spontaneously. Okay? In order to know whether a reaction is happening spontaneously or not, we need to look at delta G value. And delta G is given by delta H minus T delta S. I should write down here, the question is a spontaneous reaction. So that's what we find out. Delta G negative would mean spontaneous. Now, I haven't given any number here, so it's a pretty qualitative thing. So here you can say delta H is negative. You can plug in any negative number if you want. So say this is negative 10, just to make your life easier. This is in this particular problem, we're giving that delta H is not negative, so I made a mistake here. It should have been positive. So let's make it positive. Delta H is positive 10, just to explain it. Minus T. T is the temperature. So it's 300 degree Kelvin. And that's always positive. Temperature is positive. Delta S, change in entropy as you go from reactant to the product. Did entropy increase or decrease? Look at here. I have 3 moles to begin with and 2 moles at the end. So number has decreased. So number has decreased means randomness has decreased. More number means more random. Fewer number means smaller randomness. So delta S is going to be negative because randomness is decreased. Now again, you can assume a number, say it's decreased by minus 10. So what you see here, this becomes positive. This is also positive. This is 3,000. 3,000. And then it's 10. So it's a 3,010. Now what would happen if I leave the temperature as a variable? If I keep the temperature here, let's write down T. So what are we going to get here? 10 is coming from here plus 10T. I don't have to assume these numbers, but sometimes it helps the students to understand the problem. So you can see here delta G is positive. That means it's been non-spontaneous. In order to be spontaneous, delta G has to be negative. So if you keep on changing the temperature, no matter what temperature I can come up with, it's always positive. So it's always positive. So always non-spontaneous. But keep in mind, the temperature in absolute scale or Kelvin scale is never negative, because absolute scale begins with 0 and can go up. It cannot be negative. So let me tell you again the answer to this question. This question is, when 3 oxygen becomes gives you 2 moles of ozone, question is, would that happen spontaneously or not? So we first figure out this delta G, which is given by delta H minus T delta S. The given information is delta H is positive, so this is a positive number. But T is always positive, it's temperature in Kelvin. Delta S comes from this reaction, where number of mole has decreased as a result of reaction. Since number of mole has decreased, entropy or randomness has decreased. And that's why we have a negative number here. I have selected 10, it could be anything, but what I'm trying to show you that when you have this set of numbers, it is always positive. Any number you can pick is always going to be positive. So that means it's never spontaneous. It's always non-spontaneous. Now practice problem number 13 is next. Some of the definitions you need to know are use of salt bridge. Why do we need a salt bridge? What is going to happen if there is no salt bridge? Now, if this is the reaction you're looking at, it's happening here and here. So this is zinc electrode in zinc solution, zinc nitrate solution or zinc 2 plus in the solution. You have copper, this is copper electrode and copper 2 plus solution. I need salt bridge. This is salt bridge. This is salt bridge. Without salt bridge, there will be no flow of electricity. So this is voltmeter that's showing some flow. So why do I need the salt bridge? Make sure you read this and find out why we need the salt bridge. It basically keeps the solution neutral so that there is no charge development on any end. And that's how it helps in this reaction. You need to know the definition of oxidation, reduction. Oxidation is loss of electron, reduction is gain of electron. Oxidizing agent that helps in oxidation, reducing agent that helps in the reduction process, anode and cathode from the reaction, anode oxidation, and ox cathode reduction, cat thread. So keep that in mind. Now let's do one calculation on delta S, or change in entropy. So that's our practice problem number 14. So delta S calculation. Now, following information is given. Delta H, or change in enthalpy, is given as 50 kilojoule per mole. So 50 kilojoule per mole is a delta H value. T is the temperature in Kelvin. If they give you in 27 degrees centigrade, so that they gave you in degrees centigrade, you need to change it to Kelvin. So by first add 273. So that would give you 300 Kelvin before you do the calculation. And once I have that, I can do this calculation. Delta S will be given by delta H over T. Now, one thing I need to tell you that this is kilojoule per mole. If I give you the mole, number of moles, if there's, so there are 2 moles of a compound. 2 moles of a compound. In that case, when there are 2 moles of a compound, you might need to multiply by 2. If it's only 1 mole, then you need to multiply just by 1, which is the same number. So if it's 2 moles, just write down 2 mole. And so it's basically you get 100 here. So it's 2 times 50, that's 100. 100 kilojoule. And I need to get it in joule. Usually that's how entropy is expressed. So I can write down 100 times 10 cubed joule, which is 1 times 10 to the power 5 joule. So now I can plug in all these numbers here. 1, times 10 to the power 5 joule. And on the bottom you'd have 300 Kelvin. So this is straightforward. So this gives me the final answer, 333 joule per Kelvin. So that's my answer to this question. So let me repeat this. In this type of question, delta H value would be given, temperature would be given, and how many moles of a compound is involved here, that would be given. If it's 1 mole, then obviously you need to multiply by 1. If it's more than 1, multiply this number by that quantity. Now practice problem number 15 and 16 has to do with equilibrium calculation. So number 15. So equilibrium constant I can get from delta G value. So calculation of K equilibrium from delta G, change in free energy of a reaction. Under standard state, you write down delta G 0. Okay, this is the reaction given. 2 SO2 gas plus O2, that gives 2 SO3 gas. Now I got these numbers, delta G F0 values, free energy of formation values from back of the book in appendix. For SO2 is minus 300.4, minus 300.4. That's going to be kilojoule per mole, so kilojoule per mole. And for oxygen is a pure element, under standard state is 0. For SO3 it's minus 370.4 kilojoule per mole. Okay, from these values I can calculate delta G0 of reaction will be given by products minus reactants. So I'll just show you one step here, delta G F0 of the product SO3. We multiply by 2 because the values are for single mole, so we have to multiply by 2. So products minus reactants. So this is the product, sum of product values minus sum of reactant values. So minus, this is the reactant values, is minus 300.4 kilojoule. Oh, first let's write down the expression so that way I think it will be less confusing. Minus 2 delta GF 0 for SO2. Again, here 2 is coming from the fact that there are 2 moles here. Now let's plug in those numbers. 2 times minus 370, this is SO3. SO3 is 370.4. 0.4 kilojoule, because kilojoule per mole cancels with mole here, minus 2 moles times SO2 value, which is minus 300, minus 300.4, so that becomes kilojoule. Now we have minus and minus, so that makes it positive. So let's have one more parenthesis here. So overall, this is what I got after doing the math. Minus 140.0 kilojoule. That's the delta G0 reaction. Now, if you look at all the expressions, delta G0 reaction will be given by minus RT log of K equilibrium. From here we can calculate, let's write down this expression more in another step. Log of K equilibrium equals to here you have 140 on the top, 140.0 kilojoule divided by RT. The R value is 8.314, T is 298 Kelvin. So let me write down those numbers. R equals to 8.314 kilojoule, I'm sorry, this is joule per Kelvin per mole. So joule per Kelvin per mole. And T is 298 Kelvin. Since this is in kilojoule, let's first write down RT. R has to be in kilojoule. I have it in joule, so divide by 1,000 to get in kilojoule. So this is going to be 8.314 divided by 1,000. That gives you in kilojoule, then per Kelvin per mole. Now let's plug in all these numbers here. 140.0 kilojoule divided by R value is 8.314 divided by 10 cubed kilojoule per Kelvin per mole. These are all per mole, so I don't need to worry about it anymore. Per mole will cancel out. This is kilojoule per mole of oxygen in this case. So this would finally give me temperature is 298 Kelvin. Kelvin would cancel out, kilojoule would cancel out, and this would give me 56.51. Take the inverse log. This is log with respect to base E. So taking inverse of that, or it's the same as getting e to the power of this number. K equilibrium equals to 3.47 times 10 to the power 24. So this equilibrium constant is pretty large. So there'd be one question like this where you calculate equilibrium constant from delta G of reaction, the standard delta G or free energy of reaction. So this is how you get the free energy from product values minus the reactant values. So product first, then reactant. Don't forget to multiply by number of moles. Then there'll be a question where cell voltage would be given. If a cell voltage is given, we can also calculate equilibrium constant. So calculation of K equilibrium from cell voltage under standard state. So we'll write down as E0 cell. So this is calculation of equilibrium from cell voltage under standard state. So it would be E0 cell at 298 Kelvin. That's the room temperature. Under 1 atmospheric pressure, 1 molar concentration. So in this particular case, there are several reactions you can think about, like zinc and copper. So zinc plus copper 2 plus, giving zinc 2 plus aqueous plus copper. So this is aqueous, this is solid, this is solid, this is aqueous. So if this is the reaction, what is the equilibrium constant for the overall reaction? Again, let me show you the expression. Again, delta G0 is given by minus NF E0 cell, that's equals to minus RT log of K equilibrium. So basically in this case, we're going to use this part of the reaction. And if I want to do some algebra here, rearrangement, log of K will be given by NF E0 cell divided by RT. So basically, this is the expression that we're going to use to calculate the equilibrium constant. Now let's find out n value and E0 cell. E0 cell has to be given. Either we give you two half reactions, two half cell potentials. If I give you two half cell potentials, you just add them up to get E0 cell. So E0 cell in this particular case E0 oxidation plus E0 reduction. That comes from splitting this reaction from the two halves. So you just add up these two numbers and then get the potential value. And in this particular case, I can give you those numbers, 0.763 and 0.337. So that gives you overall 1.10 volts. So depending upon whether we give you E0 cell or we give you individual half cell potentials. If I give you individual values, you add them up, split the reaction. So let me show you how to split the reaction. Zinc and zinc 2 plus, zinc solid, zinc 2 plus aqueous. And to balance the charge, I must have 2 moles of electrons. So that's going to be my 1/2 cell. And that would be oxidation, so E0 oxidation. That value would be given to you. Now, other half cell would be copper 2 plus aqueous plus 2 moles of electrons. That's how it could be balanced. Copper solid. So that would be reduction, E0 reduction. And these two values will have to be given to you. Say for example in the question I didn't give you the E0 cell, rather I gave you individual half cell potentials. Then this would be 0.763 volt. And the other one is be 0.337 volt. So overall, E0 cell will be given by 1.10 volt. So we just added these up. So overall reaction will be, you can obtain by adding them up. So you're going to get same as this reaction. Zinc solid plus copper. So we can double check that your balancing is right, and this is going to give you this 2 electron 2 will cancel out, so you have zinc 2 plus aqueous plus copper solid. So this is the overall reaction. Now why we did this? Because we wanted to know how many moles of electrons are being transferred. That goes into our expression. So n equals to 2, which is number of moles of electrons being transferred from 1/2 cell to the other half cell. So now I have all these values to plug in. So I'm going to now use this. 2 moles of electron, 2 moles of electron. Each electron mole would have 96,500 coulomb. That's per mole of electron. Then E0 cell, we got 1.10 volts. Divide by RT. Again, R has 8.314 joule per Kelvin per mole. 8.314 joule per Kelvin per mole. And temperature is 298 Kelvin at room temperature. It's under standard state. Okay. Now here, something I need to point out to you, coulomb times volt, that makes joule. So that joule cancels out with joule at the bottom. So let's write down here. Coulomb times volt equals to joule. So what I got, I'll just write down my final answer that I got. 85.7 here, 5.7. And then you take this as log with respect to base E. So take the inverse log, which is e to the power, this number, K equals to, K equilibrium equals to, this is equilibrium constant, 1.64 times 10 to the power 37. So that's the equilibrium constant that we got. So I'll give you 2 such questions. In one question, you'd be calculating equilibrium constant from free energy of formation, delta G of, from free energy of reaction, which we get, free energy of reaction we get by using free energy of formation. Free energy of formation you get from back of the book, which I've shown you in last example. I think that's our practice problem 15. And here we are showing you from voltaic cell, from cell voltage, how we can calculate equilibrium constant. So first we split that into two half reactions so that we know how many moles of electrons are being transferred, and that is N that goes in this expression. And we need to know the cell voltage, and either you have this half cell potentials given, then you add them up to get cell voltage, or I'll give you just the cell voltage, then you don't need to worry about this addition. Just use this number in this expression and then get your final answer. So this concludes our third review session for Chem 112.